All right. Okay, let's go. Very good. Matrixology, lecture 5. We're doing it. There's a lot in this course. You guys did pretty well in that first assignment. Let me press the magic button. So I'll give you these things as we go along, little histograms of scores, and we'll distribute. I've got piles of. Okay, so we're going to sort this out as we go along. But I have your assignments here. I have covered all of your scores, so I'll put them out in batches and you can come up. And I'll put them out alphabetically and you can grab them at the end of the lecture. Solutions as well, so you have to... My brain is kind of gone by the end of a lecture, so someone may have to tell me that I have to do that. So please remind me. All right, so I'm going to distribute this stuff here. So going forward, I'll ask you to put a cover sheet, I think, on your assignments with your name at the top. So I'll give you some instructions for that. It'll make it a bit easier, right? Okay. And if you could sit alphabetically. No, I'm kidding. All right. God, that would be great. Or change your names. We could get it. Anyway, all right. So some professors give random numbers, so we're not going to do it. That's rough. Let's see. So yeah, so there you go. You'll get your grade distributions. There are some statistics at the top, averages and max and so on. And those things will appear as we go along. All right. There is, what else is going on? There are tweets, of course. There are always tweets. I put up some extra help on the weekend for some of the matrix wrangling we did on Thursday. So you can look at this. These are 5-minute long videos. I have to yell at these people. 5-minute long videos. Just telling you it's about some extra goodness there. These are really fundamental things to know about multiplying matrices together. We talked about them abstractly. One of them has an example that I didn't get to do in the class. Yeah, all right. And assignment 2 is due on Thursday. Exam 1, or challenge level 1, is the week from Thursday. Exciting. Is that a bad thing? It's very cold outside, so like, is that? Okay, all right. All right, what are we doing? You tell me. I'll try to get enough sleep too, so my brain is okay next time. AX equals B, that is our game. That is what we're doing. Somehow this whole course is about AX equals B. That doesn't make any sense, but it's true. And we'll have I touched on this at the end of last lecture. We started on this, how to solve these problems when A is square, right? So square matrices are cool. Turns out square matrices are amazing. Okay, so I can't use up all my special yellow chalk. So these are square. N by n square, that's where we are. We'll stay there today, just with square matrices that will pop back out to rectangular ones, right? So A in general is rectangular. I'll give you a method for finding A to the minus 1. We're going to go through this in a couple of different ways. We'll go through an example. It seems a little magical. The inverse just unfolds. There's really deep, crazy stuff involved with inverses. But this is an inverse, it's a product, right? So we had A times a vector, this kind of notion that it could do something to it, like rotate a vector and that sort of stuff, right? The inverse then is going to rotate it back the other way. That's a good, simple example of thinking what an inverse might do. How the inverse and pivots are connected. So pivots are funny things. We've started to uncover them. There were some questions early on about what are these objects? We'll see a connection there. So this gets deeper and deeper as we go along. More secrets will come out, especially on Thursday. I can't tell you the whole truth. You're not ready for it. But all right. Okay, what am I doing? Yeah. Okay, off we go. Good. I pick up the piece of paper. I've created a jigsaw for myself, which I will put in a better order up here. All right, okay. So, off we go. So, very important, A is square for today. Right? Let's make sure we have that at the start. N by n. Our m becomes an n. We sort of do that. We throw the m away and we say n by n. And so this is just a little recap. if we have a to the minus 1 and ax equals b, right, then ax equals b is solvable. It's a very important thing. This is great. This is where our course could end, but it doesn't. We must keep going into the forest. N by n, n by 1. I'm reading Harry Potter for like the 4th time to my second daughter, and now and then I'll just say, and then Voldemort jumps out and kills them all. And that's it. You know. It helps me. She thinks it's funny. All right. The end. Okay, so all right. So this is so we can't always do this, and we don't always have square matrices, of course. All right. Let's see. So important thing here. You know, and why? So why? This is very easy. We take ax equals b, and I want to do this over and over. Make sure that this is always in your heads, right? We always do the same thing to every side of it. Doesn't matter which equation in the world you have. You always do the same thing. You add 2 to both sides. You add 2 to one side. You add 2 to the other side. But with matrices, we have to be very careful with order. This is pre-multiplication, pre-multiply both sides. And it's important to think, when I'm just writing these things, this could be a billion by a billion matrix, right? It doesn't matter. This is an n by n matrix. N could be any number you want, a Googleplex, whatever you like. It's got a different color. OK, so this guy, there's going to be some sneaky little proof things. That's the point of the inverse. You multiply it with, it's A inverse times A is the identity matrix. This guy is just sitting over here. What shape is this thing? It's a matrix times a vector. What is this thing once we multiply them together? What do we get? What sort of, we got numbers in boxes. What sort of a box? A vector? Yeah, good. N by n, n by 1. Good, they match up. Resulting shape is n by 1. So that's, we've got a vector here. This is just the identity. Again, it's an n by n times n by 1. So we end up with x equals, right? We can't cross this. You don't want to think about crossing out. It's this operation just gives you back x. So yes, x equals a to the minus 1b. So this is solved. And so for every b, there is one x. That's an important thing here. This is a one-to-one mapping. That's what. It's another, if you have that language in your head, so there is a unique solution. So this is key, big deal. Unique solution if a to the minus 1 exists. Right? Every b, if you can think of it like this, every b can be made from one x. There are two things in this statement. It can be made. You can make that b, right? That's what this is doing. It's saying, I want an input into this little factory, feed it in this side, right? Feed your, well, let's not use bad analogy. Feed something into A here. It's going to munch it up, and it's going to produce B over here. Nice sausage. Okay. All right, so that's good. So it's not, and I said these things, just to recap, it's not easy to find the inverse. And it'll turn out that we don't want to do it, generally speaking. If someone comes around saying, I have inverses for you, they open the jacket, and they say, oh, they're bad people. All right. Go away. If they have triangular matrices, then you should talk. OK. I'll be arrested. OK, let's see. OK, so. Couple of things. Let's just add a few pieces in here. So let's say just some observations. So let's say we have AB inverse, AB minus 1. What is that in terms of A inverse and B inverse? Is that true? I did a bad thing. What did I do? It's a bad choice. I'm not a bad person. I just made a bad choice. Okay. I have children. Order matters. Order matters. Very good. So this was a bad thing to do. And it's really equal to B inverse A inverse. Right? So let's think about this. So if we're multiplying, so we observe, right? So let's do it together. So B minus 1, A minus 1. This blob times AB, that's the right thing. You have to reverse the order because these two hit each other. Very good. And this makes B inverse identity B. Identity times anything. This way or this way, it's the same. Doesn't matter. So this is equal to this, equal to this. B, and these two guys punch each other. Good. All right? So and in general, ABC, same thing. There are some other kinds of things that we do to matrices that sometimes do this, sometimes don't, etc. Okay? Good basic thing. Right? Good. Shall I say this now? Yeah. Okay. Okay, so here's a big deal. I can't quite remember what I said last time. Big deal. If, I don't think I did this. If, what's this thing? What's this ridiculous thing that mathematicians use? There exists. Yeah? I think I heard some. People say they know the secret things. There are handshakes and all sorts of stuff. There exists. Spot of Freemasonry. All right. If there exists an x not equal to 0, right? This is very important. I'm not writing a 0 here. I'm writing a 0 vector. That's something that trips people up early on. This is a 0 vector. And it's the same shape as x. Right? If this is a 30 by 1, this is a 30 by 1 with zeros in it. It's not just 0. You never say a matrix is 0. Okay, if this is true, such that, use some of this 19th century kind of language, such that AX equals 0. So this is going to be a really, really spectacularly fundamental kind of thing. We're interested in AX equals B. It turns out that driving a lot of this is AX equals 0 is a huge, huge equation. So this is a crucial equation for us going forward. You can put little stars around or whatever you want to do. But I'm still in the middle of the statement. So if there's an x for which this is true, A times that x, it sends it to 0. It crunches it, right? A annihilates x, if you want to give it the physics talk. Then we'll know, and this is, again, it's all for n by n's, then a to the minus 1 does not exist. So that's, we'll be tying these things backwards and forwards, right? We'll be going from inverse to how many solutions there are, to whether there's all sorts of things. But this is one way, this is one connection. So why is that? So here's a tiny little proof. I'm not even going to, so reason. So let's say this is true, right? We have this is true. Assume AX equals 0 for x not equal to 0. Is it clear that if x is the 0 vector, what happens if x is the 0 vector? A times the 0 vector has to be A, right? So little note here. Can I do NBs? Little Latin, nota bene. No one does that anymore? Okay, sorry. So note A0 equals 0 always, right? Then you can think of this as saying I want the 0 of the first column, 0 of the second column, 0 of the third column. Turn off the viola, turn off the tuba, please turn those off. Zeros. Okay. The cello, we can turn the cello. Okay. So assume this is true, and then, right, and a to the minus 1 exists. So this is a clever thing we like to do with proofs. We've got all these things. These are all true. What are we going to do now? Let's use them together. How should we wield these objects? I'm going to play around and see if something explodes, right? So this is what we're going to do. We poke it with a stick and see if it explodes. All right, so we take a, x equals 0. We're very, very good people, so we always pre-multiply. It's like putting away your socks, whatever it is. We're going to do this. We can do this, right? Right? We can do this. Okay, fine. So this is the identity. Identity times x is x. X, this guy, 0. But this is a contradiction against the way we speak. The world explodes, right? The world explodes and scene. All right, so that's the end of it. So this can't be true. These things can't be true, right? It's a Joss Whedon situation. Okay. Okay. Do not discuss Buffy. Okay, all right. So let's see. So this is a funny little thing, and we did a tiny little proof here, just a tiny little proof, and that sort of thing you can do over and over again. So we've got some idea about inverses and how many solutions there might be. It's starting to get together. So what else can I show you here? That's good. That's good. Okay, one more thing. These are I know these are kind of general things. Then we'll get into a machine way to a mechanism for finding inverses. Okay, this is another important thing. So let's imagine we have this. You have a problem on your problem set now, I think, or your level, which kind of does it get at this? Okay, maybe not. All right, so let's see. Imagine we have this. A times, I'm going to say Z R equals the identity. So given A times a matrix equals the identity, and there's some other matrix, Z times ZL, we'll call it, or Z if you want to be really silly. It doesn't rhyme, so it's kind of a shame. So if you have those two things, so what we might call these is a right inverse for A. And it's true that sometimes you only have that. And it's true sometimes you only have this guy. So that's more complicated. This is a left inverse because it comes from the left. So let's do some sneaky things again. Always with the sneaky things. Say thank you to our monks. But it's, again, just simple little couple of line manipulations, right? Yeah. Just hit the ball in that little hole over there. It's easy. Okay, so let's take this one. Space it out a little bit. ZR equals identity. Again, do the right thing. Socks in the right drawers. We're going to just multiply both sides by the same thing. Same thing. And we're going to take this ZL, right? We know these two things. This is all we know in the world. We've forgotten everything else about our names and everything. We know these two things, and we're going to combine them. Pre-multiply. You could do it in other ways. This is just one way to do it. What can you tell me about? So the left can collapse in some funny ways. So what's a good way to collapse that left one? What we've used so far is this is true, and then we've pre-multiplied both sides by ZL. So we know this too. So what if you take this piece of information and use it here? Yeah. Yeah. Yeah, that thing? Yeah, right. Yep. This is the identity times this whole blob times ZR. Right? From our second thing. And this is ZL. What can kind of go wrong is you say, oh, that's the identity, and then you get ZL. You know, like you sort of get confused. But we're just going to do the right thing. And you think, OK, so identity times something, it's the same thing, equals ZL. So if this is true, and so these things have to, and therefore they're equal to the inverse of A. So if you have something that undoes A from the right and another one that undoes it from the left, they have to be the same thing. That's just true. A bazillion by bazillion matrices, which is kind of good. That's a lot more work than trying every matrix out, right? A lot of boards. Yeah. Groovy. Grooviness. OK. OK, good. So I think that's a good bunch of little things that you can, yeah? OK. So here's the plan. Let's compute inverses. Which are kind of weird things, right? They are weird things. It's kind of nutty, right? So if we have, yes, what did I do wrong?
So if inverse of A exists, that's always true that you can create a function.
Yes. So by definition, that's what the inverse of A does. That's really important. I'm going to put it here as just as a reminder, right? So let's put it in here. This is a good point. Reminder. A to the minus 1 times A equals A times A to the minus 1 equals identity. Right? If A to the minus 1 exists, this is what it does. It's the object that does that. Very good. Good. So think of it just think of a rotation by 90 degrees. So a matrix that rotates a vector by 90 degrees. You can either rotate it back and then forward, or you could rotate it forward and then back. Let me do the visual thing for it. Right? You can go this way and then this way, or this way and this way, and you come back to the same place. They undo each other. Good. And when we're numbers, it's a third times 3. 3 times a third. We don't really care. We're like, fine. But order matters. But we want this. They commute, right? This special word. Good. So we're going to use, let's compute inverses. We employ, so we don't have to learn anything more. We have to think about how this works. The gauss-jordan elimination. Right? That's supposed to be elimination in a clever fashion. A clever fashion, right? We're going to construct something and play with it, but we're going to use Gauss-Jordan elimination. So let me remind you, AX equals B. This is our original problem. We go down through Gaussian elimination, row reduction. That gets us to UX equals C. And this guy is upper triangular. Upper triad. And then we had a step where we kept going, and we'll come back to this in great detail as we go on. But there was another effort where we kept going, and we got to Rx equals D, and this is Gauss-Jordan. And this is where we eliminate everything. We get rid of, we make as many zeros as we can. It's kind of the general way of saying this, right? So this is as many zeros introduced as possible. Zeros as possible. I'll just give you that. It's a little bit vague right now, but yeah. R is sort of the essence of A, right? It's a kind. Matrices have these these magical essences inside of them, and there are eigenvalues and pivots and all sorts of things. And this R is one way that if you look in the right way, that's what's inside. I will persist with taking pictures. I have to write scripts. Okay. I'm just doing this. Sorry. Okay. Good. So this is what I'm speaking broadly. Let's start with an example. Wow. People don't erase very well today. Me. Okay. Good. So let's just sort of run through the mechanism. So here's the mechanism. And then we'll figure out why this works. And again, we'll kind of operate with this very general statements. It could, again, be for million by million matrices, which is very powerful, right? Okay, so we're going to have, here's your question, right? You're sitting in an exam, you're having a great time because it's matrices, it's just fantastic. And then you come across this question, and you're overjoyed, because you know how to do it. 3 minus 2 minus 2, 4. It is not obvious straight away it just should not be obvious to you what the inverse of this thing is. Some things, you can figure out, you can guess at. It's not immediately obvious. I mean, you have to have practice with these. So given this, find a to the minus 1. So here's the setup. Again, it's always, what am I doing? It's always n by n's. We've got a 2 by 2 here. 2 by 2. So here's the setup. Always do it like this. And then we get to bring our whole row operation thing back in here. 3 minus 2 minus 2, 4. Put the identity matrix here. And we'll work out why this works. I just thought I'd go through the example first. Pretty crazy. It's like the augmented matrix where we put A and B next to each other. So this is akin to A, B. So that's, there are all these things we've done before. We can just bring them straight back in. So that's the augmented matrix. That's how we did, right? We used this to get from AB to UC, the Gaussian elimination. Right? We got rid of the x's. The x's are messy things. You don't want them everywhere. You just want numbers in boxes. Numbers in boxes are awesome. Okay. What am I doing? All right. Okay, so we do this, and this is, in general, this is a identity. And this is n by n, and this is n by n. Right? So if you have a 30 by 30, you're in hell, you've done something wrong, and today's job is to invert a 30 by 30 and burn for a while. Then you've got to put a 30 by 30 over here. I mean, who cares? It's hell, so you're in trouble, right? But that would be really bad. That would be really bad. But you put a 30 by 30 identity matrix over here. So it becomes, in general, this whole thing is an n by 2n rectangle. We set this up. We row operator of phi. Right? And we'll get into exactly how we do this until we reach this shape. Right? So we row operator of phi until we get to 1, 0, 0, 1, and then whatever's on this side. We mess around with this thing until we get the identity matrix. So we do this kind of weird thing. We undo this side, unravel it, and then we don't worry about what's happening over here. And then at the end, this thing, I promise you, will be a to the minus 1. Which is bananas, right? I mean, that's completely silly. Total magic. Of course, it's not magic. Totally bananas. I mean, I can't tell what you think, but I think it's kind of, that's odd when you first line that up. It's like, what do you mean? You get right? So you just go, you worry only about this. This is our focus. We only care about row operations on this thing. We're just trying to make whatever's in here into the identity, and we get to this. So it's this guy ends up as, maybe I can do it here, identity a to the minus 1. Nuts. Totally nuts. But awesome. So, all right, let's do it. Let's see it. Let's do these row operations. As I said, it's more than just getting to U. It's more than just making a triangular matrix. We're going all the way with our Gauss-Jordan elimination. Can anyone say anything about what will happen with pivots here? You know, and I haven't explained why this works, but what we have to get to is the identity on the left. When can we not get to the identity on the left in terms of pivots? Right, so if one or more pivots is 0, toaster row, right? So one or more pivots being kind of 0 or absent or away or vanished or in another matrix, like went to Bermuda or something, like it's not there, then that corresponds to an inverse not existing. So there's a tie, right? We're going to get more and more of these ties. And some of them are really weird. Okay, let's illustrate. Okay, all right, I can do this too. This is board, you're all bored. This is board 3. We'll call it excitement, the black excitement. Okay, all right. Okay, we're going to start with this maniac, and we've just made this crazy Frankenstein thing. We'll just glue this guy over here, and then we'll do all our nice row operations, and we're only our focus is here. Focus is here. Yes, this is great. Oh my God. Okay, good. First row operation. You should write it down. What is the first row operation? Look, there's one from 3 lectures ago here. R2 prime equals R2 minus something times R1. Always, always. We always write down this shell, right? Always. What is this guy in here? It's a little curly L subscript. L, oh, okay, good. You're telling me the answer. Yes, this is L21. And good. And it's minus 2 over 3. This thing on the bottom is first pivot. Champions. All right, good. I wonder if you can have deflated. You can have deflated matrices. Yeah. You should definitely have video cameras on your matrices to make sure that when the investigation comes. Okay, all right, fine. So we're going to do this. We're going to subtract. So what does this end up as being? Minus 2/3. So we're adding 2/3 of the first row to the second row. So I did tell you that in general, I'll give you problems where there are lots of nice integers and so on. It is unavoidable with inverses that nasty things appear to some extent. And there's a reason for that. Okay, so let's do it. So we still have the same first row, unchanged. Minus 2 plus this guy plus 2/3 of this guy gives us 0. Let's write in a different color. 4. This is going to hurt, right? So this is 4. Let me write down here so I'm not going to destroy myself. So it's plus 2/3 is all of this. So plus 2/3. Did I get that? Times minus 2. Agreed? Right? So this is 4 is 8 is 12/3. Yeah? So this is 12 minus 4, so this is 8/3. So yes, fractions. This side is easier to start with. It gets more and more messy as we go along. But 0, and it's going to be plus 2/3 times 1. 2/3. Well, right here, 0 plus 2/3 times 1. And then 1 plus 2/3 times 0 is 1. So that's our, yes, what did I do? This thing? I'm just telling you, this is some monks died, and this is what they left these notes, and they said, this is how you do it. I'm going to explain how to do it in the next, after we do an example. Yeah. So we're going to go through the scary place, and then we're going to say why we had to go through this. Right. So it's the identity matrix. Yeah. So if it was a 3 by 3, it'd be 1, 1, 1, all zeros. Otherwise, and so that's what this. Yeah. So you're right. Totally right. You just pick up a big identity matrix and go sploop. And if it's a 17 by 17, which you're very likely to get because 17 is awesome, you put a 17 by 17 identity matrix. And I'm going to explain how this works, but the idea is you are trying to get an inverse, so you want that the shape of this thing has to be the same shape as that. 2 by 2, you need a 2 by 2. So let's keep going. It's a 2 by 2, so there's just this one row operation. To clean up, we've got this. So now that's Gaussian elimination. We're done. Right? So this is actually U. That's U, as in U x equals C. Right? So we've done that. But we keep going. We're excited about this. We'll explain why we do that. So R1 prime is R1. This one is for the chop now. We always use pivots to get rid of things. Our second pivot is this guy, 8/3. So we're going to use this pivot to remove this one, right? Right. So next we use second pivot to eliminate -2. The -2 here. Right. So it's R1. It's minus this thing times R2, same business. This is now, this is actually not L12, right? This is not a real thing. We're not going to get to that actually. So this is for later. As usual, we have more later about this. We only call when we're doing row reduction, when we're creating U, we only call these little special L's. There's a reason. So that's just this little side note. But it's still the same process. What do we have on the bottom? 8/3. And on top, we have a -2. Yeah. The pivot goes on the bottom. Yeah, the pivot, it's pivoting. You're using it's your strong point. That's your base. So this is the thing we're going to use this guy, and if this was a bigger matrix, we'd use this one to eliminate things below and above. So pivot 2 here, D2. The one who's in trouble, -2 is in trouble. Barney Rubble. Rhyming slang? Anyone? Rhyming slang? Yes. All right. Barney Rubble is trouble. And then you get rid of the rubble. That's important. Yeah. All right, good. So we need them for matrices. We need one for matrix. Okay, so let's see. So what is this whole thing? This is a -2. My God, what is that? Okay, yes, good. So this whole thing is -3/4 and then a minus sign, so it's going to be this whole bit here is +3/4. Just to help us a little bit, especially people with old brains like mine. So let's then, we're adding 3/4 of the second row to the first row. Yeah? All right? Easy here because we've already got a 0 here. So 3/4 of 0 to this one, it's just 3. Let me try to use the same chalks. So this is 3. We're changing this one. We're leaving the bottom row unchanged. So 3 -2, 2/3, 1. Wow. Yeah. That's a 2/3, 1, and that's a 0. What is wrong with my hands and brain? 8/3. Yep, thank you. Okay, we're adding 3/4 of this to this. So 0 times 3/4, it's the same thing. 3/4 of this guy added to this one. Let me write it here so it's not 3/4 times 8/3. That's what we wanted to do, right? So it's working out. So minus 2 plus 2, so this is 0. This one's easy to do. So this is plus 3/4 of this one, so we get 3/4 here. I failed in my chalk mission. Okay, 3/4. 3/4, 0. And we have 1 plus 3/4 of 2/3. So these are nasty little things. They're not that bad. What's up? 3/2. Good. All right, good. 3/2. Okay, so we're nearly there because we've got a diagonal matrix here, zeros here. And so you can see what's going to, so we had to do 2 row operations to create zeros here in a 3x3, right? We have to do 3 below the diagonal and 3 above it. We'd have to do 6. We talked about this the other day. It gets nastier. We get more and more to do. Grows up, it goes like n squared. I wouldn't give you more than a 3x3. So we're nearly there. Now we have to divide by the pivots. Something we don't do with U, but we do with R. So last step is divide by the pivots. And so we'll write that as a little row operation. So it's R1 prime is 1/3 of R1. R2 prime, it's a bit funny, but it's 1 divided by 8/3 of R2. Right, so this is, just to put it what this is pivot 1, which we write as a D. This is pivot 2. Always the last step. And you're dividing the whole row. So we're dividing this row by 3, this row by 3/8. So let's do our thing. So the first line is going to be 1, 0. Dividing through by 3 is going to clean up this one. And this one, it's a 1/2 and a 1/4. Hopefully I've done this right. 0, and we can think of it as multiplying by 3/8. So that would give you 1 here. So the plan. 3/8 times this one is 3/8 times 2/3. 1/4, yep. And then 3/8 times this times 1 is just 3/8. So the claim is that's the inverse, which is funny. I mean, we're using a method we have in our heads. You can do this for arbitrarily large ones. Computers can do this pretty well. And we're kind of going to get inverses out of the way. We're going to use them in certain ways with elimination matrices, and then get into AX equals B, the solution to that, in a deep way. So we're coming back to AX equals B. But let's just check this is true. First of all, you want to clean things up. So what's a good thing to pull out of this matrix to tidy it up? An 1/8, right? We pull an 1/8 out. Yeah, good. So we'll pull an 1/8 out. This. Let me think about that one. Yep. And I want to say something about this in a second. So this is a 4, 2, 2, and a 3. This 8 is actually a special number. This is and we pulled it out. We just saw it sitting there, so we pulled it out. We could have pulled out 16. We could have pulled out anything. I'm going to tell you, and we're going to come back to it. We're going to see it, especially in the third set of 4 weeks, that this is another magic number for A. It's called the determinant. Again, because we use words from the 19th century, and we would write the determinant of A equals 8. So this is very much a more later situation, although I'll probably touch on it some more. This is a more later, lots of more laters. So the determinant, we haven't even talked about what this is, but what would be a bad kind of determinant? 0, right? So that's going to connect to a pivot being 0, one or more pivots being 0, Later, one or more eigenvalues being 0. I'm just going to say the words, right? But the determinant being 0, bad situation. So let's check. Let's check that this crazy thing I've told you works. Let's try it. So we've got an eighth, 4, 2, 2, 3, times, what was our original one? 3 minus 2, minus 2 and 4. So multiply those guys together and see what you get. Either it works or all of reality is broken. Okay. Possible. Let's have a look, right? So 4, 2, the dot product here, we get a 12 minus 4. That's 8. 4, 2, you can see that they're orthogonal, which a word we'll come to more and more. 4 times minus 2, they're at right angles. 4 times minus 2 is minus 8, plus 8, 0. 2, 3, 3 minus 2, 0. And then a 2, 3, we get a minus 4, plus 12, 8. We had an 8th out the front, 1, 0, 0, 1. And you can check the other way, right? And check. Works too. So why does this work? This is a weird thing to have done. So why does this work? Okay, so why? And so that's it. That is the universal approach to this, right? So why does this work? So mechanism, and now we'll go for understanding. So why does this crazy approach, crazy mechanism work? Let me give you a couple of ways to think about this. I'm going to erase these things. Right. So it turns out these are AX equals B problems again, although there's a better, stronger way to think about it. But it is kind of amazing what you can turn back into an AX equals B problem. Okay. Okay, good. So you think you can do this at leisure? Yeah? Very exciting. Okay. All right, so why? So let's think of it like this. So here's the idea. Let's solve A times Z equals I. We're not putting them in boxes. Let's solve this problem. And I talked about Z being on the right, Z being on the left, but let's solve this problem and see if we can get it to work. So I want to note that this doesn't. So if we get a solution for this, this doesn't obviously, and that's a word that I have used for a long time, or said is a very silly word, but this is, I think it's right. It doesn't obviously mean Z A equals I. Right? We will get to this. We will sort this out. You have to do a little thinking, a little extra thinking to show that that is absolutely true. But we're only going to find this is really just the right, this is actually just the right inverse. We've already said these words today, so it's okay. It's really just the right inverse. Okay, let's think about it a couple of ways. So, we did some of this matrix wrangling stuff. Let's write it like this. Let's take the 2 by 2 example. Hopefully you can see how this will generalize to 3 by 3, 4 by 4, 5 by 5. We'll also treat it in a way where you don't have to write things down like this. A times Z1, Z2 stacked together. Let's imagine that that's what they are, right? 2 columns. This is going to be the identity. And you can go back and check this. I gave you this extra video online. That A times, and we talked about it last lecture, A times Z1 and A times Z2. The way matrix multiplication works is that on the left-hand side, we end up with A times Z1 in that column and A times Z2. Okay? A goes in there and gets that one, A gets this one, and they become the 2 columns. So again, n by n, n by 1, these guys match. This whole thing is a column vector. And what's on the right-hand side? This is 1, 0, and 0, 1. And if you're thinking in calculus world, this is I hat and j hat, right? And if we go up to n by n dimensions, they're the unit vectors along all of the axes. Yeah? Good. So these are unit vectors in x1, x2 space. We don't use x, y, and z. We use x1, x2, x3, x4, x5, because we're happy to have x77. All right. So understanding this particular way that multiplication works means that you can identify these two. This column is equal to this column. And the second column here is equal to this guy. So we get 2 equations. So we get A times Z1 equals 1, 0, and A times Z2 equals 0, 1. These are AX equals B problems. Right, we started with this is not an AX equals B problem. This is a matrix times a matrix equals a matrix. These are all square, right? So this is n by n, n by n. That's a little bit scary. That's a much bigger game. These are AX equals B problems. We know how to deal with these, right? So it's like yay, right? So this is yay, easy. So row reduction. So this is kind of getting us the plan. That's why we would do it. So we could separately solve these, right? You could do row reduction on this one, and then row reduction on this one. But you can put them together and solve them at the same time. So we could solve AZ1 equals 1, 0, and AZ2, I get it right, equals 0, 1 separately with row reduction via row reduction. But we'd use the same operations, right? The way we reduce A in both cases, we do the same operations here as we do here. So you might as well combine them. You might as well do it all at the same time. But it's much easier to combine row reduction, right? A doesn't change, right? A is the same in both equations. So when I said it was an augmented matrix, it really is an augmented matrix. So we really do solve this guy, 1, 0, 0, 1. It's really a super augmented matrix. I'm making these words up. Super augmented matrix. So let's think about, once we get these solutions, yeah, they're going to do exactly the right thing. Once you've got Z1, A times Z1 gives you 1, 0. A times Z2 gives you 0, 1. So then you put Z1 and Z2 next to each other, and that's your inverse. So in general, if you find the vector that A multiplies to give you one of these unit vectors, then you put it in the right slot, and you put them all next to each other in the right slot, and you'll make the inverse. You you're solving very, very special AX equals B problems. They're very special B's. 1, 0, 0, 1, and in general 0, 0, 1, and 0, 1, 0, 0, 0, 0. All right. So, we've talked about it. So a big deal is this only works if A has n pivots. Right? And sometimes you'll see this, you'll see it in Strang's book. None are missing. They haven't gone to watch the World Cup in Australia. All right. None are missing. They has n pivots. They're all healthy. You can't undo it otherwise. What am I going to tell you next? So that's good. We've got our plan. And let's think about what we did. So this feels a little bit funny because, I'm kind of having to ask you to think about the Zn, n by n, but we're sort of doing it bit by bit. So we still have this problem that it's not necessarily clear that Z times A is the identity. I know everything else is clear to you, but it's not obvious that that's true. So we have to deal with that. All right. Okay, let's write this then. So back to our example. So let's empower ourselves with elimination matrices. Right, we need to know more. So we need to sort some more things out. So let's go back to elimination matrices and empower ourselves here. So is it all here? Can I point to this? Yeah, so here are our row operations. Here's another row operation. And then there's this division by pivots. So let's encode those with matrices. Okay. So back to our little example. This guy, it was A equals 3 minus 2 minus 2, 4. And then we found the inverse, 1/8. Sorry, 1/8 here. Yep. 4, 2, 2, 3. I'll tell you some more things about this in a little bit, if I can remember. So the row operations via matrices. So the first one, let's write them down. So the first one was E21 equals 1, 0, and this is a plus 2/3, 1. In general, this is of this form. It's 1, 0, minus L21, 1. And this corresponds to the row operation R2 prime equals R2 minus 2/3. Minus 2/3 like this, times R1. So that was our first one. We had another row operation, which we can write as E12. We're using the second row to clean up the first row. That will look very similar. 0 here. And the general form is, well, let me not write it like that. We had a 3/4 here. We ended up with a plus 3/4. And this corresponded to R1 prime is R1 minus, and we had all this stuff. Let me write it. Was minus 2 divided by 8/3, like that, times R2. So these things. So there's our right? I've been trying to, well, we've introduced elimination matrices. We've said that they do the same as just kind of writing down the row operation. We're actually using a multiplication to do the job. Okay, so we've got this one, and there's one other row operation that we did, and then division by pivots. Let's think about this. So I'm going to write down a matrix that we'll call D in general. And so we'll write down the pivots on the diagonal. This is an important kind of matrix. 3 8/3. 3 8/3. This is growing in awesomeness, as I can tell from your happiness. D1, 0, 0, D2. Am I lying? What am I doing? Is it okay? Yeah? Okay. Yeah, so this is, right, this is use row 1 to clean up row 2. And it's also the multiplication, yeah. Very nice, right? Yeah. Magic will happen because of that. Okay. Good. Well spotted. So we're just going to make D. This is true in general. It's a diagonal matrix with the pivots along the diagonal. Now we'll have. They don't have to be on the diagonal. D can be a. Yeah. All right. Yeah. No, that's right. That's right. Yep. Okay. These are the pivots. All right. So this is pivots on what we call the main diagonal. The main diagonal. Now we're not just sort of putting them up on a shelf in a nice place. This turns out to be a functional matrix because what's the inverse of this matrix? What's d to the minus 1? So this is a general question. So and maybe I should have prefaced this with some, I guess I could have. But anyway, all right. Anyone guess what this is? Yeah. So we're going to invert, we're going to turn everything upside down. So let's do that abstractly. So if you have a diagonal matrix, you flip everything upside down on the diagonal. And we'll look at that a little bit because I think we have to dig into this one. So in this case, it's 1/3, 0, 0, and 3/8. So diagonal matrices, the inverse of diagonal matrices. Let's have a little detour to mention this. Matrices is the matrix with the inverses along the diagonal. Now, a creeping dread comes over me that I haven't said this word diagonal matrix. Have I said that? Have I said that? Maybe not. Diagonal matrix means that it only has non-zero numbers along the main diagonal and square. Let me say that as well. Diagonal matrix. Square matrix, n by n. Zeros here, non-zeros, only non-zeros. There can be zeros there too. Only non-zeros are on the main diagonal. So I guess I'm introducing a few things there, if I haven't said them properly before. All right, main diagonal is going down the head. This is not a diagonal we care about. We don't care about this or this. It's this one. So the identity is the best, simplest diagonal matrix. So the inverse of the identity is, right, you flip over the ones and you still get ones, so that all works, right? Okay. So we had this last step where we divided the first row by D1 and the second row by D2. And that's the same as multiplying by this matrix. So this encodes, this whole thing in here encodes row 1 prime equals 1 over D1 times row 1, and row 2 prime equals 1 over D2 times row 2. So now we've got all our row up. We're not just sort of running down. This is what I did to the matrix. It's like, here's a little mechanism that you put your matrix in one side, it pops out the other side with either this thing done to it first, then this thing, and then this thing, right? Okay. So why are we doing that? Well, okay. Do not attack the board. I secretly do this so I can think. Okay, so, all right. Here. So on this piece of paper, it has A, D, E. See, there's no B. I don't. I'm teaching you in a nonlinear fashion. All right, the irony is lost on me. Okay, so, all right. Boom, we've got this guy. So, okay, so. All right. So we're going to apply all these guys. The upshot is our elimination, our Gauss-Jordan activity looks like this. Row reduction can be written as, right, the thing we did can be written as this. We have A. The first thing we did to it was multiply it by E21. This guy. That's the first thing we did. So we're going to snug it right up there. And then we're going to do E12 to it. We're going to multiply by E12. E12. And then we're going to multiply by D minus 1. And if we do all of those things, this is equal to we're taking A, we're doing all this row reduction. What did we do when we got what? This is one of the vowel things that I have trouble with. A, E, I, O, U. No one knows what it is. What's it? Identity. Identity? Good. Right? This was the job of row, in this case, because this works because all the pivots are non-zero, actually. But we did we cleaned up the second row, then went back to the first row, cleaned that up, then we divided through by the pivots, and we got to the identity. So what's this blob here? Yeah, right. So it's a potential. This is doing the work of A inverse. So let's just call it ZL to start with, right? Right now, just say we've got a left inverse, right? Let's call it this left inverse. We know if we have a right inverse and a left inverse, we're good. Yeah. So it turns out, yeah, so this is kind of odd, but the elimination matrices with potentially this guy, with always a pivot matrix, inverse, put together in the right way, will actually make the inverse of A. Before, we had all these things written down as sequences of actions, right? They were written down, they were like a recipe, a code, right? Now they're in boxes that do things to each other. And we're not even going to multiply, we're not multiplying A now, right? We're going to actually multiply these guys together by themselves. We're not going to do that row operation. We're going to sort of do the second row operation to the first one, if you like, and then. yeah, once we've uncovered them, we've got them all here, but then we take them off by themselves, multiply them together, which is not what we were doing before. Like, that's kind of a weird thing to do, right? Yeah. We've got all these actions, and now we're going to multiply them together and make a big operator. Yeah, which is this 2 by 2 matrix, right? Good. So we have that. And of course, if we go back, and if I erased it, oh, I guess I did. Yeah, but we solved this, right? We solved A times Z, and we'll call it R now, equals identity. We solved this. That's what we were getting. So we actually have this. We have a ZR, and we have a ZL. Right? So we got this from our row reduction, and our row reduction activities encoded as ZL. We solved this for ZR. So because ZL equals ZR, so from before, right, and from before, we know that ZL equals ZR equals A inverse. So there was a concern at the start, you were worried, that you could have just found a right inverse, right? Because we're solving A times a blob equals the identity. It's not clear that that blob put over here will do the right thing, will undo A. But the argument up here is if we go back and look at the actions we took, we can say, oh, well, we can combine those actions, which we've encoded as matrices, and see that that is the left inverse. That's undoing A from the left. And we have that, so we have a left inverse, a right inverse, and we showed before that they have to be just the one and the same. Yes. All right. So there are a few things, there are these two big things going on in this lecture. There's how to do it, and there's how to understand it, right? So you can definitely get the how to do it thing. You've got a little mechanism, and then I want you to really think about this. Okay. That's pretty cool. I like that a lot. So let's address the horrors of zero pivots. No, we won't. I'm going to scribble it down. All right, let me scribble it down, and then we'll come back. Scribbling down, people. Right. So, last piece. Man, talk too much. So, if elimination, and we've said this out loud, but we need to write it down, gives one or more pivots equal to, I'm going to say they're equal to zero, or missing, then we can't get from, that's a from, A identity to identity A to the minus 1. Because of that last step, right? D to the minus 1 because D to the minus 1 does not exist. Right? You'd have to have a 1 divided by 0, which is fine if you're doing some crazy physics, but it's not here, it's not happening. It goes boom. Goes boom. All right, so that's just a little piece to end with. Assignments are due on Thursday. And your assignments can come back right now. Thank you, people. Great, great. All right.
Thank you.